Hello! Last lecture we talked about random samples. Now we will assume that random sample comes from a multivariate normal distribution with two parameters, that is our mean vector and our covariance matrix. And we will show that under this assumption that the random sample is actually coming from a multivariate normal distribution, then we can obtain maximum likelihood estimators. So the maximum likelihood estimator for the mean and the maximum likelihood estimator for the covariance matrix. So estimator means that this is actually a random variable. This is also a random variable. However, when we have a data, then we will call those estimated vectors as estimates, and we will assume that each element of that vector is now a number, as it is an estimate. So estimator is a random variable, estimate is the estimated vector, so a vector contained of numbers or a matrix of numbers. Okay, how are we going to obtain those maximum likelihood estimators? Well, we need to maximize the likelihood function. Okay, what is the likelihood function? So it is this function L that is defined to be the joint probability density function of the random sample when you look at this L as a function of those random vectors, of those vectors. When it is a function of those vectors, then it is a joint probability density function of the random sample or of the sample. It maybe is not a random sample. Okay, in this case, because we have that this is a random sample, it means that all of these vectors are mutually independent. Okay, in general, when we have a sample, they do not necessarily need to be independent. But in our case, we will almost always have a random sample, so almost always those random vectors are going to be independent. So as a function of those vectors, it is a joint probability density function, and as a function of the parameters, so now they're not fixed. If we look it as a function of our vectors mu and sigma, then this is a likelihood function, but those vectors are fixed. Okay, in one case joint probability density function, in another case it is our likelihood function that in this case we want to maximize. Okay, as we are given the random sample, they're independent, so we know that it is actually a product of marginal probability density functions. Each of these vector has a multivariate normal distribution. Say that the probability density function of this random sample, because they have the same probability density function, all those vectors, is denoted by f. So this is our probability density function, so our f. What we actually want to do here is to get some nice representation of the likelihood function and then just maximize it. This is why we will do a couple of steps. So first step is to write it as a product of marginals because we have a random sample, as I mentioned, so they're independent. Next equality follows just from the definition of multivariate normal distribution. What our definition says is that the probability density function is given exactly like this. So we just substitute. Next, we need to use the properties of multiplication or a product, and just what we get here is a sum because of exponential function, and here we just have n because we multiplied it n times. In the next step, we will use something that we mentioned in introduction class. So what we mentioned is a trace of a quadratic form. So what do we use here? Well, first we know that the quadratic form is a number. So say that this is x transposed ax. Just imagine for a second. So this is a number. We know that that number, x transpose ax, is equal to the trace of this matrix, which is obvious as it is 1 times 1 matrix. So that number is going to be equal to the trace of that matrix. But the following that we use is actually that the trace of quadratic form, so a trace of x transposed, so x transposed a x is equal to the trace of ax x transposed. So basically this x transposed goes to the right side. Okay, so this is a property that we did not prove, but it stands, and we will not prove it. If you are interested, you can see the proof in suggested literature. The proof is not that hard. However, we'll just use it, and in that way we get our sigma inverse of our sigma. It exists because this is a positive definite matrix. Our x, so our x and our x transposed. Okay, what we also have is our sum. So this is our sum. We will actually, because this is a matrix that does not depend on the sum, we can just write sum and this matrix can change positions. So we will get this expression here. Okay, so here we used a property from introductory class. Next is some matrix algebra. So what we want to do is write this sum in a simpler form. So how are we going to do that? Well, it is not shown here, but it is simple. Just add and subtract in each of those brackets the average. So x average, x bar. By doing that and multiplying corresponding pairs, you will get the result immediately. So this part is just some matrix algebra. What you need to do, the trick, is to add and subtract the sample average. So with x with the bar, and you will get this result. Part 3 is actually again usage only of the properties of trace. So what we have here is a trace, okay, of one and another one. Okay, so what we have here is a matrix, and this one, the complete here, is a matrix. So it is going to be trace of a sum will be a sum of trace, so trace of this one plus trace of this one, but multiplied with sigma to the power of -1, so the inverse of sigma, because as you see, this is in front, this part, and then there we have a bracket. Okay, and then we will just use the same property that we used here, so of the quadratic form. So how we got from here to here, we will just do that again, but for this part. So we have ax transpose, we will instead write that x transpose ax, and we have that n. And then we will use that the trace of a constant is just that constant. So this is now a part that does not have trace, but we still have multiplied with e to the power, so it is still to the power of e. Okay, so we got to this point using properties of trace and some matrix algebra. What we need to do now is maximize this function in respect to our mu. So this is what we want to estimate, our mu. And that mu is only here. So what we need to maximize is only e to the power of -1 divided by 2 and this part. Okay, so this is the part that we need to maximize. Basically, what we need to do is maximizing this part here. Okay, what we know is that sigma is positive definite. It means that our sigma to the power of -1, or the inverse of sigma, is also positive definite. What does this now mean? That our quadratic form, so any, by the definition of positive definite matrix, any quadratic form for non-zero here, it should be greater than 0 because it is positive definite. So the only way that this expression is going to be 0 is if this vector is 0. Because if this vector is not 0, then by the definition of positive definite, we know that this is larger than 0. And in order to maximize this, we know, because now that this is always larger or equal than 0, it is larger than 0 if this is different than 0. But if this is 0, then this is 0, and that is our maximum. So just to repeat, when we have this exponential function of some parameter, let's say a, and that a is larger than or equal than 0 always, we know that the maximum of this function is actually 0. You can always check this by finding derivatives and second derivatives to see if this is maximum or minimum, but this is obvious as this is exponential function. So the maximum can be when this is 0, not can be but is when this is 0, and this is 0 only when this is 0, and this is true because this is positive definite matrix. Okay, so by just taking that x bar minus mu is equal to 0, we see that x bar has to be equal to mu. So our maximum likelihood estimator of mu is going to be this average, so x bar, but instead of the fixed values, we have a random variable. So because this is the estimator. If we want the estimate, we will write it like this. So this is the part that you should distinguish. Even though we explained those three equalities, you may want more explanation, which you can find in literature. So the explanation, but yeah, it should be clear. So this is just the maximum likelihood estimator of the mean vector. But what is the maximum likelihood estimator of our sigma, of our covariance matrix? Well, to prove that, we will need a theorem or a lemma to help us prove it. Okay, so that lemma or theorem without a proof is given here. So what does it say? That if we have a positive definite matrix and we have a constant that is larger than 0, then this number, so this is a number, we can compare only numbers, okay? So 1 divided by a to the power of b, e to the power of minus 1 divided by 2, trace of this expression, is smaller or equal than, so what we have here is not a, but b, 1 divided by b to the power of b, so our second matrix, times this number. So 2b to the power of pb, e to the power of minus bp, and this inequality is true for every positive definite matrix A. So this is true for every positive definite matrix A. Equality stands for this type of matrix. So this matrix is positive definite because B is positive definite and B is different than 0. So it is larger than 0. So we have equality only when we choose the matrix like this. So let's see how is that lemma going to help us find our maximum likelihood estimator. So what we know, what we already proved for the likelihood function is that it can be written like this. So this is our part 1. So this. So we'll just continue from this, but instead of our vector mu, we will look at this likelihood function only as a function of sigma, because we already know what is the maximum of in respect to this parameter. So just by substituting it, we can find the maximum for sigma. Okay, so we, instead of mu, will use mu hat, and our mu hat is actually our x bar. So you can either write mu hat, okay, or x bar. So remember that this is now a matrix B, and this B is positive definite matrix, and also this A is going to be positive definite. Okay, so taking this choice for sigma to be A and this to be B, we can actually see that this is maximized when we choose that A is equal to 1 over 2B and our matrix B. So by this lemma and this choice of matrix A, so A is sigma, we know that it is equal, or it is maximized because it cannot be more than this. Okay, we need to take that our sigma, so now this is a function of sigma, okay, and we want to maximize it, and it will be maximized because it is, as you can see, smaller or equal than this expression always, and it reaches that expression for this choice of A. So we need to choose that our sigma, or the maximum likelihood estimator, we need to choose it to be 1 divided by 2b. So our b is n divided by 2. So 1 divided by 2 times n divided by 2. So we just follow this expression. Okay, times b. And in this case, because now we are talking about estimator, we need to write these various big or capital letters. So this is actually our estimator, so our b. Okay, so we obtained the maximum likelihood estimator easily using this theorem that we just stated without proof. And when we substitute these capital letters for small, we will get our estimate. The correct way to prove that this is actually maximum, and actually perhaps the easiest way, is to use gradient, or to take partial derivatives in respect to mu and sigma. And in general, when you have multivariate sample, you would need to check gradient if it is positive definite matrix or negative definite, depending if you're looking for a maximum or minimum. But as I said, we will try to avoid multivariate calculus, so this would be enough for you to know for now. And what you should do more. So you should just prove that it is positive or negative definite, but just keep it in the back of your head that there should be more calculus. And this is how we proved that how are our maximum likelihood estimators given. Next, we want to see in what value, so what is the value of the maximum. So when we substitute our two maximum, so because this is a function of mu, when we substitute those two values, we will actually get this expression. So some constant, okay, does not matter, some constant, you can substitute to see, times generalized variance. So our generalized variance is to the power of minus n divided by 2, so here. Okay, and this is determinant, so we know that this part is going to be to the power of p, because this is a constant that is in front of the estimator. So it would be here. Okay, in order to get s, when you substitute, we already substituted to find unbiased estimator. Okay, because this is our unbiased. So go and look how it looks. So because we have n minus 1 divided by n, let's say in each row, and we have p rows, n minus 1 divided by n is going to be to the power of p, because we have determinant here. So this is just a simple property of determinants. So what we get is some constant times generalized variance to the power of minus n divided by 2. Okay, so we can see the connection between the generalized variance and our maximum likelihood estimators. Okay, it is important to mention that the properties of the maximum likelihood estimators in univariate case, such as invariance property or sufficient or jointly sufficient statistics, holds even in this multivariate case. So the invariance property holds, as well as that this pair is jointly sufficient statistic for our parameter, in this case two-dimensional parameter mu and sigma. Okay, the sampling distributions of our x bar and s are similar to the ones in univariate case. So we had that x bar in univariate case has a normal distribution with mean mu and variance sigma squared divided by n. So similar as this, because this would be sigma squared divided by n. And for our sampling distribution of S, we have in univariate case that it is a chi-square distribution, so n minus 1 S squared, okay, has a chi-square distribution. However, in multivariate case, we would need to generalize this, and by generalizing, we get actually a distribution that we call Wichern distribution. So in this case, we would have, for example, Wichern distribution with p or m degrees of freedom. So this Wichern distribution, as we know that chi-square is a sum of our independent squared normal standard normal distributions or random variables, here we would have, because what is squared in our multivariate case, it is actually, for example, x transposed. So it would be our squared. So sum of x transposed, where x's have a standard multivariate normal distribution. Okay, so actually not s, but n minus 1 s will have a Wichern distribution depending on the notation, degrees of freedom. So for example, p minus 1, or if we have n minus 1, then it will have n minus 1 degrees of freedom. Okay, same as in univariate case, we had n minus 1 s, but we had only chi-square distribution, not Wichern. And in this case, when we have from multivariate normal distribution, those two are independent, x and s. Also, you can look in the literature about the properties of Wichern distribution, also how the probability density function looks like, and in the end, we should mention that for example, central limit theorem and some of its corollaries stand even in this case of multivariate distribution or the multivariate sample. So if we had like any independent observations, x1, x2 to xn, let's say, with some mean vector and covariance, okay, then we will know the distribution as given in univariate case, that square root of n times, for example, our mean minus mu has approximately normal distribution. So in this case, approximately multivariate normal distribution with mean 0 and covariance matrix sigma. But this is a case when n is large, the same way as in univariate case. So this will be it for the maximum likelihood estimation. See you in next lecture. Bye.